understanding where data is coming from, understanding why we collect it, comes down to this model right here. So being able to understand how to set up your experiment is going to be the basis of whatever data you collect, of whatever data you analyze, and how you approach that data or those data. You have two groups. In any kind of experimental investigation, manipulative investigation, you're going to have that experimental group, the control group. You've got the dependent variable, and that dependent variable is where you're going to be making comparisons of data. So what's different between the dependent variables in these two groups? So think back to the Radish Seed Lab. What is your dependent variable? What did you measure? What did you count? Or what are we seeing as the output? That done their germination, right? Germination of the seeds. How many of them germinated? Germinated, right? And so we're just going to compare a number of seeds germinated in both cases, in the control group and the experimental group. What did we keep consistent between the groups?
Number of seeds.
How many seeds we used, right? I guess I should write germinated, right? What else did we keep consistent? What else did we keep consistent? Very good. Light. A lot of people missed that one. So there's all these things that were exactly the same. I'm just going to write ditto marks for both the experimental group and the control group, and the only thing that differed between them, the only thing that you will ever have that can differ between your experimental group and your control group is the independent variable. It is the one factor that you are trying to isolate to see if that is the thing that has some effect on your dependent variable. This is the only difference right here, is that independent variable, and seeing how does that one single solitary thing or aspect of your experiment lead to differences in what you measure in terms of your dependent variable. If you have more than one independent variable, you get to do advanced statistics. And that sounds fun, right? Yep. No, one variable. Keep it with one. Got it? Manageable? We're okay with that? Okay. And so we take this one or several treatment levels of an independent variable, apply them to the dependent variable, and collect data. For our seed lab, what data did we collect specifically? It was quantitative. Why? What was it? The number of what? Okay, so when we look at quantitative data, it is counts or measurements. And so what is the purpose of any kind of quantitative data? It is to make comparisons between your experimental and your control group so that you can see what is the impact of the independent variable. So our purpose here is to help you make a conclusion. Okay? But that's not the only data that you took. Did you get any other data? Okay, I know no one actually has a camera that does that, but did you get any other data?
Pictures.
Yeah, you got the pictures. And what is the purpose of that? Well, qualitative data is descriptive. I keep standing right in your way. Sorry, Becca. So we've got this descriptive data, and why? What's the purpose of even bothering with it? If quantitative data is the one that's going to help us get to our conclusion, why waste our time getting qualitative data? Any ideas? So when we're taking these descriptive pieces of data, this qualitative data, if we see that everything seems pretty consistent across the board in terms of describing what you see, okay, maybe that helps validate your conclusion that you're getting from the quantitative results. But I want to look at the seed lab in particular because somebody noted a very interesting thing about their data. And what they noticed is that some of the seeds at 0% were fuzzy. Now, you can't really quantify fuzz without having a microscope and seeing how many particles of fuzz there were. But what you can do is just take a mental note of that. Because if you see that there's more germination at the 0% salinity, but you also see that there's this other factor coming into play, that there's more fuzziness at 0% salinity. Maybe that's an indication that it's not the salinity causing germination. Maybe there's some other factor that you are not considering that now your qualitative data is going to help tune you into. So maybe the extra mold that's present in those that is growing is helping. I don't know. So that data is just there to give you more support, more direction, more misdirection, but sometimes that's an important part of the scientific process. Okay? I want to talk sample size just very briefly. If I decide that I want to find out the average intelligence of a high schooler in the US, and I decide this table, you three, there it is, sample them, find their intelligence, measure it somehow, even though we won't talk about that. But I decide that I'm going to measure their intelligence and say, okay, I'm done. Sweet. The average American teenager has an IQ of 146. Pretty impressive. This table is on point. I mean, American children are on point. Look at you guys. You must be smart. Is there anything wrong with my sample size or with the sampling that I did?
Yes.
A lot of potential issues here. No offense, I think you're all lovely folks, but do I think, first of all, that these are the most representative people in the country? No. So when we're sampling, it's going to be important that it is random and representative. Do you think that my selection of 3 individuals does a very good job showing a bigger trend? Okay. The goal in any kind of science is you've got this pot of data right here. It's all the data that exists about a particular question that you have. So every teenager in America, their IQ is represented by this pot of data. Now, if I just take that, how do I know that that's a good indication of what the rest of the pot of data is going to look like? So what happens if I increase my sample size?
That's better.
So maybe I do 4?
No. You gotta get bigger numbers. I suggest 10%.
The goal in any kind of scientific investigation is to maximize your sample size so that you can most accurately represent the total population. Are you ever going to be able to even sample 10% of all American teenagers? No. Maybe you get 0.01%, but that's still probably better than, 4 people from one class in one little town that really doesn't matter that much, right? So larger sample size. So when we have a larger sample, it is more representative of the total population, ergo, more indicative of the results that you're really looking for, okay? On your lab, I would certainly expect a wee bit of discussion of sampling. What are the samples that you took? How many did you take, right? For your group, each only got 5, so we'll talk about that, okay? So now we have to talk graphs. We're going back to the discussion that we started with in the very beginning. And I will tell you that I have the easiest way to graph ever. And for some reason, it keeps escaping kids. So I think here's what happens. There's other ways that they're kind of the exceptions for graphing. So it's just never taught as simply as it could be. You ready for this? Boom. You're going to take your x-axis, and that is going to be your independent variable. You're going to take your y-axis, and that's going to be the dependent, because guess what? In math, y depends on x. The independent variable is going to be the one that changes, and the dependent one changes in response to it, right? So always start by figuring out your independent dependent variable. If you know that, then you just have to graph that. Horizontal axis is going to be your independent. Your vertical axis is your dependent, okay? So as long as you're putting your independent variable along that horizontal, that x-axis, and then the dependent on the y, you know you're starting off in good shape. The next question that I have is, when do you do a bar graph and when do you do a scatter plot or a line graph? Raise your hand if you know, but you just can't really put it into words. Like you feel like, oh, yeah, I know when to do them. Okay? So, what's the key here? In the textbook, there's a picture of a graph. You look at the graph, click on the little buttons, like I said, to make sure you're always clicking on those individual images. And so there's a hint there. Actually, there's the answer there. When am I going to pick a bar graph versus a line graph / scatter graph? So here's that simple formula for you. Start with your x and y axes, then decide if you're going to do a bar graph or a scatter plot. If it is categorical, meaning you did not measure the independent variable, then it's going to be categorical. If it is continuous and you measured the independent variable, then you're going to put it in as a scatter plot / line graph. We can kind of distinguish that in a sec. Okay? So for this lab, is salinity continuous or categorical? Did you go out and measure salinity? Did you measure it? Or did I give it to you? Did anyone find that the salinity of the liquid that they used was 1.2789% saline weight per volume? No. You just took the one that was at 1 and poured it in. So that, in this case, is going to be categorical. Now, if I had sent you outside and said, I want you to find what is the relationship between salinity and plant growth, and you went out and you tested the soil, and then you tested the height of the plant, well, you're measuring two different things now. You're testing the salinity, but on a continuous level, and the height of the plant, again, continuous. So when you're actually measuring the independent variable, then you're going to use this graph here, and you end up with all these different data points, right? Maybe a line of best fit. Otherwise, we're sticking with a bar graph. Okay. Exactly. What was I saying? Let's come back to that. Don't really care there. Let's talk formal lab. Let's get you through this piece. You'll probably want to come back to this in future lab reports and refresh yourself on this. So, hello, future class period 1, 2, and 3. I don't even know what I'm doing with my life. All right, moving on. So some important information to keep in mind. First, we need to understand the types of data. Okay, so you're doing a lab. Step 1, figure out the independent and dependent variable. Step 2, figure out your hypothesis and all that crap from that independent and dependent variable. But you're going to collect raw data. Data.
Raw data.
And this is just what you're measuring. That's it. No manipulation done to it. You keep it raw. You're not mathematically manipulating anything anywhere. Just show me what you got. This is going to be both the quantitative and the qualitative, although usually you'll put the qualitative data as a little footnote underneath the table. Your table headers should include your independent, dependent variable, some in there, either the headers or the row titles. Make sure you're including your units only in the headers or the row headers. I don't know what those are called, so run with it, okay? So in other words, your units are either going up here or up here. They are not going in the body. if your data, and I'm saying this very deliberately so you're listening, if your data are collected in a way that groupings do not matter, then do not include groups. For example, in your data, what you guys collected when you were pulling out the radish seed information. Was there anything that inextricably linked your 0% to your 1%? No. Okay? In my weight loss example, if I'm giving you all a weight loss pill and I want to see how much weight you've lost, is your data before and your data after, are those connected? Should those stay together? Yes. But it doesn't matter what group collected the data. You don't need to find a way to indicate this is group 2 of period 3. It doesn't matter. It doesn't impact your data. Okay? All right. So from your raw data, you're including a table or two, whatever you need to include your raw data, and then manipulate it. You manipulate it in some kind of way that you can help pull out trends. So, differences are always good. Ratios, rates. Most of the time you guys will probably use averages. It's easy enough, but yes, an average is a manipulation of the data. Ready? Here's where I do the other really important thing where you tune in if you haven't been. Only graph manipulated data. If you don't have enough data to manipulate and you're tempted to just graph your raw data, then you don't have enough data to be doing anything with anyway. Your sample size is too small. So it is only if you can manipulate the data that you should be graphing in the first place, and it is only this data that you are graphing. If I see graphs that look like this, 0%, group 1, group 2, group 3, group 4, group 5, group 6, group 7, and then 1%, and it's like group 1, 2, 3, whatever. It gets so overwhelming with crap. There are other ways to show variability, but for right now, your best bet is usually just to show an average of all of the data that you've collected. You're going to make sure that you put it either in the same table as what you had your raw data is, but clearly distinct, clearly separated, clearly indicated, or you can put it in a new data table. I don't care either way. And only then are you going to actually make your graph. Another big thing that I want you to remember, your tables, your figures, your graphs must be standalone. You must be able to have the picture in your lab, and I should be able to know what it is without reading the rest of the lab. So, figure 1. How seeds germinated when exposed to various... Good. Figure 1, our data. Not good. Figure 1, a graph of our data. No. Okay? Make sure that your anything, whether it's a chart, whether it's a table, whether it's a graph, I don't know, whatever, go with it. Make sure you're giving it a figure, title, a number, and a title that actually allows it to stand on its own so that if for some weird reason that picture got separated from the rest of your document, I can still figure out what's going on. And when I say referenced, you should be pulling back. Hey, as seen in figure 1, blah, 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 blah. Because if you can't reference it, then why are you putting it in there? The only exception is your raw data. I've literally gotten AP Labs, sorry if this was from one of your classes, Lindsay, that are like 30 pages and people brag, look how long my lab is, woo! And there's 14 pages of graphs. Like, dude, that's not helping me understand the trend. That's making my head spin and I kind of want to vomit. So don't do that. If you have more than 2 or 3 figures, it's probably too much. Or graphs, sorry. More than 2 or 3 graphs, probably too much. Just include the ones that are worthwhile in terms of referencing.